Okay, so I want you all to round it off to 6927 Newton. Okay, in terms of Newton, forget about what? The decimal point. Are we clear? Okay, what is 0.9 of a Newton? Any idea? So 1 kilogram is equal to how many Newton? Anyone? 9.81 Newton, right? Am I right? It cannot be equal. Huh? Can I say 1 kilogram is equal to 9.81 Newton? Right. What I'm trying to highlight is this. Okay. Can someone tell me what is 0.5 Newton in kilogram? What is it? How many kilogram? So 0.5 is equal to m multiplied by 9.81. The mass will be equal to what? 0.05 what? 1 kilogram. Can someone tell me what is 0.051 kilogram? Can someone give me a feel what is 0.051 kilogram? Hey? No, I'm not angry. I'm just trying to you all to visualize. 0.051 kilogram is like when you fart, understand? So when that's the case, that's why you round off your what? Whenever it's 0.2, you just round it off. Are we clear? Okay, so don't give me like, oh, Eugene say mathematically, we have to have 3 decimal places. But when it's important, you don't put it in what? 3 decimal places in Newton. Are we clear? Remember, why not 3 decimal places, but know about your fart. Are you clear? I know you guys can't remember, don't give a toss about it, but anyway. Right, so FAC is 6927 Newton. Right, we do another example. Is this example clear? Yes, sir. The end of the rod is pin. What? Okay, so rope AD is dependent, from here is independent of rope AC. Yeah, that will not, okay? Are we clear? That's a weird question, you cheeky sort. We'll not change the fact about this, right? We'll not change the fact about how we construct the free body diagram, will it? No, right? Okay? Wow, you guys are very technical. I like that. Okay, let's do another problem. This is the last problem we're going to do. Then we are going to do crazy sort of buckling. Okay, so this is the next problem. This problem is pretty straightforward. I like to think so. Okay, okay. I do apologize. This problem is not so straightforward. Okay, I'll tell you why. So example number 2. Okay, we are going to look at an example number 2. I think it's a very interesting problem. Okay, let's look at example number 2. Now, example number 2, I like to highlight. I will spend more time on this example because there is a sense of optimization over here. Yes, it is on Avenue and is on week 1. Sorry, it's on week 2 on Tuesday. You have that or no? Right? You have that, right? It's on week 2. Oh, sorry, week 3 Tuesday. I beg your pardon. Okay, it's on week 3 Tuesday. Okay. So this question is a bit tricky. It has to deal with what? Optimization. Okay, let's look at it. An aluminum column of length L and cross section has a fixed end B. Okay. And support a centric load at point A. Okay, so this is, they declare that at point B, this is fixed. And over here, they declare that this is a centric load. Okay. Right. So when they declare this, is basically telling us when it's centric load, we can basically use P is equal to pi squared EI over L squared. Basically, that's it, or LE squared. Okay, so it's going to be based on the two smooth and rounded fixed plate restrain NA from moving in one direction, moving in one of the vertical planes of symmetry of the column, but allowed it to move in the other plane. So what does it mean down here? Okay. So we are going to follow the transformation of what you see over here. Okay, X, Y, and Z. Okay, if I were to sketch a transformation, this is the transformation that you see. Okay, X, Y, and Z. So the first thing that we want to analyze is we are going to analyze, okay, we are going to analyze the XY plane. Okay, we are going to analyze the XY. So from this case, we are going to sketch. So this is my X, this is my Y, and then this will be my rotation about Z. Okay, so that is my Z rotation. So when we sketch that now, it will look like this. Then you have a beam. And this over here is fixed. So when you see this, you can visualize that, right? From the figure, right? So I'm going to label up here point A. And I'm going to label here point B. And a good practice to write now is over here, the second moment of area is going to be in the what? ZZ orientation. And why is that? The deformation pattern will look like this. Okay, this is how the deformation pattern will look like. Okay, so the curvature is in this direction. The radius, the curvature of Z is also there. So we are going to focus on IZ. So with this in mind, we know at the bottom, moment is not equal to what? 0. At the top, moment is equal to what? 0. However, at the top, X is also, sorry, Y is also equal to what? 0. Okay. Whereas at the bottom, X is equal to 0, Y is equal to 0. And we know that this is known as fixed. And the other end is what? So from here, one end is fixed, one end is spin. We know that LE is equal to 0.7 what? L. How do we know that? One end is fixed, the other end is spin. One end is fixed, the other end is spin. One end is fixed, the other end is spin. I copy and I paste. This is how we know. And this will be provided. Okay. Are we clear? So now we look at the other orientation now. The other orientation that the structure will buckle is on the XZ plane. And this is your rotation about Y. Okay. So now we were to sketch this now. Now our member will look like this now. Or our structure will look like this now. Yes, sir. Say it again. The XY equal to 0 means you don't allow it to move. Where are you? Right? You don't allow it to move. I did not say it's the forces. So it's a bit confusing. I do apologize. So I will write this more. Fx is not equal to 0. Fy is not 0, but the position x and y is equal to what? 0. Okay. So for this case, x, fx, I have to be careful over here. Fy is not equal to 0. Fx is equal to 0. This is because y is equal to 0. X is not equal to 0. Okay? Thank you for clarifying that for me. You get a pint of beer. So we know over here, you will have I'm drawing this top part is because of this, okay? So you have this. Now the structure now will deform in this orientation. With our fixed, this is exaggerated. So for this case, over here, this is our what? Still our fixed, but the other end is our what? Free, yes or no? Because if we were to zoom in at point A, right, the structure can move where? Yes or no? It can move left and right, right? So it's free, you cheeky soul, unbelievable, right? So when that's the case, right, over here, we know that moment is not equal to 0. Up here, moment is equal to 0. Fx is equal to 0. Fz is equal to 0. That's why it's free. Over here, Fx is not equal to 0. Fz is not equal to 0. So in this context, our LE is equal to what? 2L. Right? How do we know? Is we look at this over here. One end fixed. And the other what? N is what? The other N is free. Are we clear? Okay. I'm going to stop here. I'm going to finish off this example on Friday, and I'll see you guys. Thank you for your time.